In this activity, we're going to be making a interval for proportion. And what we're going to do is try to figure out how often do Hershey's Kisses land on the flat side when tossed. So what we had our classes do is we had them basically take 25 Hershey's Kisses and toss it twice and count how many in the tosses landed flat. If you want to do this, make sure they're, if they fall on the floor or in the groove, then you pick them up, roll again. So anyways, Mrs. Overman got 16 out of 50, so that's 0.32. So my point estimate would be 0.32. And what I did is I was creating this large paper. You'll find it. So here's the large paper I created that I had on the classroom front. And you can see there's the point estimate for different tables. Now in my paper, you're going to notice that my 0.32 is not in here. So I was just kind of doing mine as a separate. So, but my 0.32 would have been right there. Also had a small boo-boo on the range there, but it was fine. It was all fine. So then, basically, so there's my point estimate. What are we trying to measure? Well, the parameter or the population is all Hershey's Kisses tosses. So if you were using Hershey's Kisses as sort of a weird coin flip, then would it be a 50-50 coin or a different type of coin? So P represents the true proportions of tosses that land flat. The sample is 50 Hershey's Kisses, 50 tosses of Kisses, lots of S's. P hat is a 0.32, and then again, answers vary here because you saw different confidence intervals. So was the sample random, and why is this important? Oh, I forgot to add in, but I still can. We shook up the Kisses and tossed them. So the reason that random is important, we want an unbiased estimate. All right. We want a representative sample, so that's usually the issue. Then, Cami keeps doing this. It drops square roots like crazy. All right. So what is the formula for calculating the standard deviation of the sampling distribution of pi hat? You recognize this. We did this when we did sampling distributions. It's P times 1 minus P all over N. N equals sample size. Yeah, most of you should know this by now, but it happens. You're like, what's N? It's the sample size. So just a little reminder there. What condition must be met to use this formula? Has it been met? So the 10% condition usually has to be met. And the 10% is for sampling without replacement. But it's not like I'm tossing one kiss and then leaving it alone and saying, oh, you're flat Hershey's Kisses. It's more like dice. So I'm actually saying we're sampling with replacement, so the 10% condition does not apply. Let me go ahead and add a note to sort it. If we were sampling with replacement, then yes, comma, 50 tosses is less than 10% of all total tosses. All right, you can keep tossing forever. All right, if we were, let me write that, but we're not. 10% condition doesn't really apply. I'm going to bug them about that. I'm like, 10% condition doesn't really apply. Okay, we don't know the value of P. That's the whole point of the confidence interval. So we're going to use our sample, our P hat. Since I don't know if it's like 50% or some other percent, I'm using what I got, which is 0.32. And then I do 1 minus 0.32, and then you can see 50 is the sample size. And I get this value right here, which is 0.660. So there is my actual standard error. Has an E here because we're doing it from a sample. Okay, from sample. All right. Would it be appropriate to use a normal distribution to model the sampling distribution of P hat? And by this, they are referring to the large counts condition. So you would just basically look how many flat landing Hershey's Kisses did you get and how many others. So the flats are successes. I got 16 and 34. So yes, my conditions are met. Now we're going to look at the empirical rule and try to figure out what's the critical value. So we are going to calculate it by hand because you guys are totally capable of this. If you look at the picture, my computer's a little wonky today. No, that's not the picture. Oh, it's in here. Yeah. So if you look at the picture here, I have the formula. P hat plus or minus your critical value times your standard deviation. So we have all the values now. We have P hat. We have the critical value. We have the standard error. So we can calculate margins of error. So that's the first thing we did. So, but how do we find the critical value? So let's go to the Statlet. You go to normal distributions and you put in, because we're doing a critical value, it's Z's. And my students were very good in first period, and they remembered that Z is 0, the mean is 0, and standard deviation is 1. We're trying to find a value, critical value, so switch that and go central. And then your area is, if we're doing 95%, you would calculate your value, and boom, there we go. Oh, there we go. The critical value is 1.96. Always use the positive one. So that's a 1.96 here. This too was from the empirical rule when we learned it earlier in the semester. And then if you switch these to 80 or 90 or 99%, so I can switch these areas. So if I want a different level of confidence, I can just switch those. 0.9, you see that's 1.282, 0.9, 0.99. So you just can do that to find your critical values. All right. Then finally, we calculate our margin of error. So that's from this part right here. Okay. So you take your critical value times the standard error, and that's your plus or minus. So what I did is I said, okay, we're doing this. You see how I have all these plus and minuses. So everyone went by hand, and there's mine by hand, 0.32 plus or minus 0.129. Then I just grab a calculator, and I say, okay, what's 0.32 minus 0.129? I get 0.191. And for the upper value, I get 0.449. So these are all the intervals. They gave them to me. And you can see only one interval, the one that had 50%, missed the true value. So we don't expect all intervals to capture the true value. Every once in a while, that's the only way it would work is we did 100% confidence interval, but that's not very helpful. And the true value was 0.35. So let me go ahead and show you how to do this the easy way. So I had 16 and 34. So I'm going to go to Statlet. And the question is, what kind of data is this? Well, it's tempting to say quantitative because we had numbers all over the place here, right? But really, what did I measure? I measured 16 successes and 34 failures. That's what I really measured. So it's actually one categorical variable. And then you can say Hershey's Kisses. And then the category will say flat. And I got 16. Not flat. I got 34. Begin analysis. And you can skip all this. It's just like, okay, well, I told you that. All right, and then there's more. Come down here to perform inference, all right? And then you go one sample Z interval. That's one we want. And flat is success. It defaults to the percent you want. So if you want to change it to something else, you can. Perform inference, and there you go. That pretty much rounds up to the same values that I shared right here. 0.191 and 0.449. So see, you could, and I actually have it here, so let's highlight. So you want to make sure, scroll down, and then let me add a note. Use, what do we call it? One categorical. To enter your successes and failures. All right, so that'll work. Okay, and then finally, let's go ahead and do some the check for understanding, and it looks like I've got some overlap here. Let's see what's going on with this. I thought I cleanly put this here. Do we have some double? Okay, so there's this. Sorry, guys. You'll live. I think I just need to do this. There we go. So calculate the interval. Let's see if I can put this so it doesn't overlay. There we go. Here's the procedure. All right, I'm going to go ahead and put this right here so you can see it. All right, so first of all, what are we dealing with? We have 55 of the 1,000 kids want to be a doctor. We want a 98% confidence interval. So you go in one proportion, one categorical variable. So I'll add that as one categorical variable. All right. Thank goodness for Scala. So that's what you have to enter. Then you scroll down to this part right here. Make sure that you do one sample Z interval. You have doctor and 98% confidence, and it will spit out your confidence level. So what does that look like? So here I have a drawing. It shows our estimate, point estimate is 0.055, right? And our margin of error, if you calculate it by hand, which I'm doing, right? Oh, well, actually, Stapplet just gives you the lower and the upper, right? So there we go. We can actually calculate the margins of error. So the point estimate is, the margin of error is just the difference between two sides. Let me go ahead and add the other numbers so this all makes more sense. 0.072. So there's your margin of error, right? There are different ways to handle the point estimate. You probably are just going to, well, you could average the two ends, or you could find the margin of error first, which is just basically take the total width, divide by 2, and you get 0.017, right? Let me switch to highlighter. And then basically, you could take the 0.38 plus 0.017 to find the point estimate, or you could just average the other two. Checking conditions on this and parameters. P is the true proportion of kids who want to be a doctor. Conditions are that it's random. Well, let's see, is it random? A random sample, yes. 1,000 is definitely less than 10% of all kids in the U.S. And this is sampling without replacement because you're not going to ask the same kid twice. Large counts, we have 55 successes and 945 failures. Make sure this is not the total, all right? That is n minus number of successes, okay, right there. So that's your failures right here, which you should know that. But doesn't hurt to point it out, right? And both are met, so we met those conditions, and then we ran the interval, and if you want me to do that again, it's 55 at 945. So I could just change these up here, edit inputs, doctor, 55, not doctor, 945, and then what do you want to be? Give me anything. All right, scroll down. We want a one sample Z interval, doctor, and I think they wanted 99%, right? 98%. So put 98 here and perform inference, and boom, there's your boundaries, which match, well, I would hope so because we got them off the stack. Last but not least, how do you interpret it? You would say we are 98% confident that the true proportion of kids who want to be a doctor is between 0.38 and 0.038 and 0.072. And there you go. And that is the last lesson for this unit.